Welcome participants to the live session for our course Applied Computational Fluid Dynamics by Professor Rajesh Ranjan sir. In this session, our experts from MathWorks, Ms. Priyanka and Ms. Nirupama will conduct a session on visualization and simulation of fluid flow using MATLAB software. We warmly welcome them. Over to you, Priyanka. Priyanka, ma'am.
Thank you, sir. Thank you so much. Good evening, everyone. Welcome to a tutorial on solving visualization and simulating fluid flow using MATLAB. I am Priyanka Shukla, and I work as an online course developer at MathWorks. The makers of MATLAB and Simulink are key products. MathWorks is the leading developer of mathematical computing software for engineers and scientists. We have over 90 toolboxes used to help scientists and engineers solve problems, visualize ideas, and create new products. Here are some industries where our tools are being used extensively: aerospace and defense, automotive, biotech, and communications, to name a few. In today's session, we will begin by outlining the engineering problem we are tackling. Imagine a pollutant spill occurring in a river. Our challenge is to detect and monitor this pollutant as it travels downstream using strategically placed sensors. We'll gain a clear understanding of the scenario, how a pollutant enters the river system, and the role of sensors in identifying and tracking its movements. To solve this engineering problem, we will be leveraging the simulation tools to model the spread and detection of the pollutant. For this, we will use MATLAB Online for our simulations. We will model the river channel and define the initial conditions of the pollutant spill. We will then visualize the initial state of a system, providing a clear picture of where the pollutant starts and how the river environment is configured. Next, we will be run the simulation to observe in real time how the pollutant disperses through the river and how it is detected by the sensors along the way. At the end, we'll summarize the key concepts covered and highlight the main takeaways from our today's session. Finally, we'll open the floor for your questions to clarify any doubts. Now, let's go to the next part of the tutorial and see what we are going to do in this session. In today's session, we are going to consider a long straight river channel with a steady uniform current flowing from left to right. At the center of the channel, a small accidental chemical spill occurs, forming a concentrated blob of pollutant. You have to predict how this pollutant will move and spread through the river over time for a downstream water quality monitoring and remediation efforts. So for this purpose, we have placed two sensors in the river. Sensor A, which is located just downstream from the spill, which is near the center of the channel, and sensor B, located farther downstream near the river bank. At the moment of the spill, sensor A will detect a sharp rise in the pollutant concentration. However, sensor B measures almost none. But as the river current carries the pollutant, the blob stretches and diffuses, and over the time, both sensors begin to register the pollutant, though with different concentration profiles depending on the flow and mixing. So the engineering problem is how to predict the pollutant concentration evolves in space and time and estimate when and how much pollutant will reach each sensor using a computational simulation. For this purpose, we will follow a series of steps. First, we will set the river domain, discretize the grid, and initialize the chemical spill. For this purpose, we will be classifying the channel boundaries, we'll construct a computational grid. We will formulate the populant blob as a concentrated circular region and then locate the spill at a selected position in the channel. The next step will be to assign a steady uniform velocity field and visualize the flow and initial concentration. For this purpose, we will be selecting constant velocity components u and v for rightward flow, and we will visualize the river flow direction using velocity vector plots. Finally, we will see how the pollutant is advancing or the concentration with time with advection. So for this purpose, we will be implementing a conservative advection scheme. Then we will track the downstream movement of the blob at each time step, analyze the deformation and stretching caused by the velocity field. Now, let's get to the hands-on part of the tutorial where we will visualize and simulate the fluid flow using MATLAB. For this purpose, I am sharing a live script with a placeholder codes. Please check your chats and download the work live script that I have just shared with you. This live script has all the placeholder codes, and during the session, I will be posting the relevant code in the chat window so that it is easier to follow along. At the end of the session, I will share the solution live script, which you can use for your future references. So to get started with the hands-on activity, please download the work live script shared in the chat. To access the MATLAB online, go to the NPTEL course page. In the course outline section, come down to MATLAB and click on MATLAB. Now you will see two options, MATLAB Access and MATLAB Training. Click MATLAB Access. If you have never accessed MATLAB online provided with this course, please complete the steps mentioned on this page. However, if you have accessed MATLAB online before, please click the link provided in the step 3. This will take you to the MATLAB online. Click the MATLAB online button to open up MATLAB online. Once you see the MATLAB online window, and you can check this by checking the URL, and it should be matlab.mathworks.com. So once you can see the MATLAB online window, right click in the file section and right click on the file section and select the option to upload files. I'll repeat, once you can see the MATLAB online window, right click in the files section and select upload files option. After this, navigate to the download section where you have just downloaded the work live script. After this, go to the download section where you have just downloaded the work live script and select the work live script. To upload the live script in MATLAB online, click on the open button. Once you see this upload files window, the live script is added to MATLAB drive. Now, I hope you were able to follow along with me and have added the work live script in your MATLAB drive. Now, scroll down and double click the uploaded work live script to open in MATLAB online. I have shared the file in the chat, but if you are still unable to access it, I will share once again. So I hope you all were able to follow along with me. And we can now start with the hands-on session for hands-on part of this session. So before we start this session, let me tell you a little bit more about LiveScript. LiveScript is an interactive MATLAB script where we can embed code snippets, text, and images in one environment. To make you familiarized with the LiveScript environment, on the top here you can see different tabs such as Home, Plots, App, Live Editor, Insert, and View. This is called the tool strip. On the left, you can see various files and workspace panes. In the live script, we have a table of contents where the different sections in the live script are linked so that you can easily click on a specific heading and it will navigate you to that particular section of the live script. So let's get started with the hands-on activities. So the objective of today's session is to simulate, to predict how the pollutant concentration changes over space and time within the domain. For this, we will use computational modeling to estimate when and how much pollutant will reach each sensor location. So for this purpose, we are considering a long straight river which has a steady uniform current flowing from left to right. And at the center of the channel, there is a pollutant block. So to solve this engineering problem, we have a series of steps. The first step is to set up the river channel and the initial spill. After we have done setting up the river channel and the initial spill, we will be visualizing the initial state to confirm the parameters that we have set up. Next, we will be simulating the pollutant transport and see how in time the pollutant is traveling. For this purpose, we will begin with a simple advection simulation and gradually introduce more advanced methods, including improved numerical schemes and volume of fluid approach to better capture the fluid behaviors. So next, let's walk through each stage with code and visualization to understand how the pollutant transport in rivers. So the first step is to set up the river channel and initial spill. For this purpose, we will model the section of a river as a 2D computational domain discretized into a grid using mesh grid. For this simulation, the domain is a square region representing the stretch of the river. The flow is set as a uniform rightward velocity, simulating the river's steady current. The pollutant spill is initialized as a circular bob of radius 0.15 and centered at 0.5 x and y. The code also uses fine grid integrations to accurately represent the initial spill's shape. So to summarize, the code, it will initialize a square domain for a fluid simulation, specify its dimension, cell sizes, and the properties of a circular object within the domain. So it will create a grid for plotting and then define the uniform velocity field where fluid moves horizontally towards the right side. So let's get started. So as I write the codes in the work life script, I will be posting in the chat so that it will be easier to follow along with me. So first, as part of setting up the parameters, let's set the values for the domain length in X and Y. I have posted the code lines in the chat. Please copy paste them so that it will be easier for you to follow along with me. Next, let's mention the domain length in Y. So Y of E is equal to 1.0. As I mentioned, we are going to consider a square domain. So that is the reason the X and the Y units are same. Next, we will specify the cell size. So the cell size for X is represented by dx, where dx is equal to 1 by 10. Similarly, for the cell size of y, we have the parameter dy, which is equal to 1 by 10. As we have considered a square domain, the cell is also a square. Next, let us find out the number of cells in X and Y. For this purpose, we are using the variable nx, which will be given as nx is equal to xe by dx. So basically, the domain length divided by the cell size will give us number of cells in X. Similarly, for number of cells in Y, which is represented by the variable ny, it is given as ye divided by dy. So till now, we have specified the grid, the cell size, and the number of cells in X and Y. Now let's define the pollutant blob. As I mentioned, we are considering a circular blob. So let us specify the circle radius. The radius of the blob is r is equal to 0.15 units. So at line number 19, you can specify r is equal to 0.15. And we are going to place this circular blob at the center of our grid. So we are going to specify the X and Y coordinates. So X coordinate is X cent, which is equal to 0.5. And similarly, we have the Y cent, which will be equal to 0.5. I hope you all were able to specify the parameters. Let's go ahead and simulate this particular section. So to simulate this particular section, come to the live editor tab. Come to the live editor tab in the tool strip and click on the run drop down. And from here, I'm sorry, one second. Um, come to the live editor and come to the section drop down. And here you can see the run section button. Currently, we are going to run this live script section by section because this live script has placeholder codes. So I repeat, as we have entered the parameters for the domain and for the circular block, we want to now add these parameters to the workspace. So for this purpose, come to the live editor tab and then come to the section drop down and click on run section. Now let's create a matrix F to represent the fluid volume fraction in the domain. The matrix size is adjusted to account for the boundary conditions, and hence we are going to add +2 in both x and y directions. Give me a second. I am unable to control this. I will unshare my screen and share again. I hope my screen is visible. So currently we have defined the parameters for the domain and the circular block. Now let's define the matrix F to represent the fluid volume fraction in the domain. So for that purpose, we will mention the variable F, which consists of zeros, and we have considered +2 in both the dimensions x and y. I have posted the code in the chat. I hope you are able to follow along with me. Next, use the mesh grid function to generate two matrices, xg and yg. These xg and yg will represent the grid of cell centers for plotting and calculation. This grid spans the entire domain based on the specified cell sizes. So let us specify the values for xg and yg. So xg yg is defined as mesh grid, line space of 0 xe nx plus 2, and then again line space 0 ye ny plus 2. This plus 2 is to consider for the boundary conditions. Next, let's initialize the pollutant block. To initialize the pollutant block, we will be using this particular line of code. If you see carefully, this line of code will be similar to the equation that we use for circle. Now, we will now define the velocity field for the fluid. We will be considering the horizontal velocity u, which is set to a constant value of 1.0, which will indicate that there is a uniform flow to the right. Whereas the vertical velocity v is set to 0, so that it indicates that there is no vertical movement. We are doing this setup as it is crucial for simulating how the fluid interacts with the circular object in the domain. So let's define the velocity field using mesh grid. For this purpose, we are using the variable max velocity and initializing it as 1.0. Next, let's specify the uniform rightward velocity as the variable u. And the non-vertical velocity, as we are considering it as 0, we are going to use the function zeros. So v is equal to 0 size of x of g. So with this, the river, the flow, the pollutant source, they are all now defined. So we are ready to visualize the initial state and verify that our setup matches the intended scenario. But before that, let's run this particular section. So in the tool strip, go to the um, you can go to the section and then click on the drop down to run this particular section. Another way to run this particular section is to click on the slanted lines that you can see. So now whatever parameters we have initialized in this particular section, they are all stored in the workspace. And now we can use it to visualize the initial state to verify that our setup matches the intended scenario. So in this particular section, we are using two types of plot. One, a quiver plot for showing the uniform rightward velocity field across the entire domain, and a counter F plot depicting the pollutant concentration. The pollutant blob appears as a circular region of high concentration centered, and the axes are labeled in physical unit, and the black box outlines the computational boundaries. So for this purpose, we will be using a code that generates two side-by-side plots to visualize the fluid dynamics data. The first subplot is for a counter plot using the variables xg and yg for the grid coordinates and f for the volume fraction values. Labels, color bar, and equal axis scaling are added for clarity. The second subplot that we have is the quiver plot. Which presents the velocity field as a quiver, that means a arrow plot, where the velocity components u and v are shown as blue arrows at each grid point with axis limit and scaling set for proper visualization. On top of the velocity field, we will use a red circle to represent the pollutant blob, calculating using the parametric equation centered as x cent and y cent with a specified radius of r. So let's go ahead and run this particular section. We'll wait for the simulation to get completed so that we can visualize the initial conditions that we have set. So now we can see the initial conditions that we have set. We have a red circle which represents the pollutant blob, which is centered at the mid of the domain. And the domain that we had specified was a square domain. Now, let's move to the step 3, which is simulating the pollutant transport. So the main goal here is to simulate to predict how the pollutant moves and spread as it carries by the river. So starting from the initial circular bob at the center of the domain, the code advances the pollutant concentration field in time using conservation advection scheme with the operator splitting. At each time step, the fluxes are computed based on local velocity and concentration gradients, updating the pollutant distribution across the grid. This process mimics how the river current stretches, deforms, and transports the pollutant blob downstream. So let's see how to set this up. So for this purpose, we have set the time step to be dt is equal to 0.005. We have selected a small time step for stability. Then we have defined the number of steps as nt is equal to 100. nt is equal to 100. So this code simulates the upwind advection of a scalar field over time, updating the field based on its previous state and visualizing the results at each time step. For this purpose, we have a for loop. In the for loop, the outer loop is for the time steps. This loop iterates over the total number of time steps, nt, allowing the simulation to progress through time. Then the current state of field f is stored in f underscore old to use for calculations in the next time step. We also have some inner loop for the grid points. These nested loops iterate over the interior points of the grid, avoiding the boundary or the ghost cells. Then we will be calculating the upwind differences. The differences of fx and fy are calculated to determine how the field changes in x and y directions respectively. Here, fx represents the change in x direction, while fy represents the is calculated but not used since the flow in y direction is assumed to be 0. Next, we will be updating the field f based on the upwind scheme, where u is the velocity in the x direction. So the term minus u of I comma j into dt by dx into fx represents the advection effect. Next, we have a code for visualization. So this particular code will help to visualize the updated field using the counter plots. It checks if the current time step is the first or if it should be plotted based on the modulo condition. The counter f function creates filled counter plots, and the draw now updates the figure window in real time, allowing for a dynamic visualization of the advection process. So overall, this code effectively demonstrates how to simulate and visualize the advection of a scalar field in a two-dimensional space using MATLAB. So now let's go ahead and run this particular section. Please observe that in this animation, as the time is increasing, the circular blob is moving rightward. I hope you are able to observe the movement of the circular blob towards right side as the time increases. You can also observe how the shape of the circular blob gets distorted. I hope you were able to follow along with me and are able to observe how the circular blob shift rightwards. So we saw that as the simulation progresses, it is important to continuously monitor and visualize the evolving pollutant field, both for validation and for extracting meaningful engineering insights. The initial circular blob, which was centered at 0.5, 0.5, is seen deforming and moving rightward, that is downstream, along with the river flow. So these visualizations reveal the evolving shape and trajectory of the pollutant. For added insight, the code can record concentrations at specific grid points, representing the sensors whose locations are marked on the plots. Plotting these sensor readings over the time helps predict when and in what concentration the pollutant will reach critical location, which is essential for environmental monitoring and response. So this concludes our demonstration of simple advection, where we observe how a fluid blob moves uniformly across the domain under a constant velocity field. While this approach captures the basic motion, it does not account for more complex scenarios such as obstacles, variable velocity fields, or more accurate numerical schemes. However, real-world fluid flows are rarely this simple. In practical application, fluids interact with obstacles, experience variable velocities, and require more accurate numerical treatments to reduce errors like numerical diffusion. To address these challenges and capture more realistic dynamics, we now move on to the advanced advection techniques. So we will introduce an obstacle into the flow field and implement improved numerical methods to represent the physics of fluid motion. This will allow us to simulate more realistic and complex fluid behaviors. To understand the impact of the spill, we observe how the pollutant concentration changes throughout the river and at the specific sensor locations over time. So for this purpose, we will be writing a code that will initialize a 2D grid, fill it with a circular blob of values representing the concentration field. Then we'll set up a velocity field, perform time stepping to simulate the advection of the blob using first order upwind scheme. The results are then visualized at each time step, showing how the blob moves through the grid. So let's get started. So here also, first we will be defining the parameters. We will be using the same parameters that we have used in the first case. So we are going to use a square domain. I am posting the codes in the chat so that it's easier for you to follow along with me. As we have a square domain, then xe and ye is equal to 1.0. In the previous case, we had selected the value of dx and dy as 1/10. But here, since we want to see a finer grid so that we are able to observe the blob more clearly, we will be using dx and dy as 1/50. I'll repeat, we are specifying dx and dy as 1 by 50 so that we are able to observe the blob more clearly. Next, let's specify the variables for the number of grid points in x and y directions, that is nx and ny. So nx is equal to xe by dx, and similarly ny is equal to ye by dy. Next, we will define the parameters of the circular blob. As we are considering a circular blob, the radius is 0.15, same as what we had used in the previous exercise. So r is equal to 0.15. Now let's specify the variables x cent and y cent for the placement of the blob. We are placing the blob in the center of the grid. So x cent and y cent are 0.5. Now we have a code to create a grid of x and y coordinates and initialize a 2D field with zeros, including the boundary conditions. So here we'll be creating a mesh grid, same as what we had specified in the last time. Mesh grid is a linspace of 0, xe plus comma nx plus 2, then linspace of 0, ye, ny plus 2. The plus 2 we are considering to account for the boundary conditions. Next, we'll be initializing the field with zeros, which will also include the boundary points. So this code, which uses the mesh grid function, it is to generate the grid of coordinates based on the specified ranges for x and y. It also initializes a 2D array or field filled with zeros, which includes additional boundary point. This setup is often used in simulations or numerical methods where a grid is required to represent the spatial data. Then we are initializing the field with zeros. So this line will initialize a 2D array F with the dimensions of ny plus 2 by nx plus 2 filled with zeros. This array represents the field where calculations or simulations will take place, and the inclusion of boundary points allows for proper handling of the edge conditions in the numerical methods. Then we have a loop code that fills the subcells, and with the values representing the proportion of each cell that lies within a specified circle. The code iterates through a grid defined by nx and ny, determining whether each cell is entirely inside, entirely outside, or partially overlapping with a circle. So for cells that are partially filled, it samples points within the cell to calculate the fraction of the cell that lies inside the circle. The resulting values are stored in the matrix F, where each entry represents the fill fraction of the corresponding cell. The outer loop iterates over a grid defined by nx, which is the number of cells in x direction, and ny, that is the number of cells in y direction. The loop starts from 2 to account for boundary conditions. For each cell, the code calculates the coordinates of the bounding box defined by the cell's position. Here, dx and dy represent the dimensions of each cell. Then we have this if condition, which checks if the entire cell is within the circle. If it is true, the corresponding entry in F is set as 1.0, indicating full coverage. We also have the else if condition, which checks if the entire cell is outside the circle. So if this else if condition is true, the entry in F is set to 0.0, indicating that there is no coverage. If the cell is partially filled, the code samples 400 points, that is 20 cross 20 grid within the cell. It counts how many of these points fall inside the circle. The fill fraction is then calculated as the ratio of points inside the circle to the total number of sampled points, and this value is stored in F. So this approach allows for a more detailed representation of how each cell is filled by the circle, which can be useful in various applications such as simulations or graphical representations. So now we are also setting up the maximum, the velocity field, the maximum velocity as 1.0. The variable u represents the horizontal velocity initialized to a constant value of max velocity, while v is set to 0, indicating no vertical movement. And we have the CFL number, which is defined to ensure that the stability in the numerical simulation. The time step dt is calculated based on the CFL condition, and the total number of time steps, that is t underscore steps, is determined for a simulation duration of 1 second. So the loop will iterate over the number of time steps, and the current state of field F is stored in F underscore old for reference during the update. So this nested loop updates the scalar field F using the upwind scheme. And depending upon the direction of the velocity u, it calculates the new value of F based on the values from the F underscore old. So basically, this code effectively demonstrates how to simulate and visualize the dynamics of a scalar field influenced by a uniform velocity field using numerical methods in MATLAB. Now, let's go ahead and run this particular section. So you can see here that the circular blob is slowly moving towards right side, and also visualize that the cells that are partially filled, completely filled, they have different color gradients. So this allows us to more effectively observe the direction of the circular blob. I hope you're able to observe how the circular blob is moving towards the right side, and how the color gradient for the completely filled and partially filled cells is changing. Now, if you observe, the circular blob is almost out of the domain, and we only have some partially filled cells now. So through these stages, uh, the code transforms an initial spill into a dynamic predictive model of pollutant transport in a river channel. This approach enables the engineers to anticipate the spread of contaminants, inform sensor placement, and design effective remediation strategies, demonstrating the real-world power of computational fluid dynamics. With this advanced advection, we have seen how incorporating obstacles and improved numerical schemes allows us to more accurately simulate complex fluid flows. This approach brings us closer to modeling the real world scenarios and highlights the importance of robust numerical methods in computational fluid dynamics. Now, let's move to the next section where we will try implementing advection using the partial differential equation. So in the previous two sections, we use the first principle approaches, which provide valuable insight into underlying physics and numerical challenges of the transport phenomena. While these methods are highly instructive and offer fine-grained control over discretization, they can become a little bit cumbersome to implement and extend, especially for complex geometries or higher dimensional problems. To address these challenges and streamline the simulation workflow, we use the partial differential equation toolbox in MATLAB. This toolbox is specifically designed for solving a wide range of partial differential equations, including those governing advection and diffusion on arbitrary geometries and meshes. It automates mesh generation, boundary condition, solver selection, and allowing us to focus on modeling and interpretation rather than the low-level implementation details. So the task is to write a code that simulates the diffusion and advection of a blob in a two-dimensional space using partial differential equation, that is the PDE model, and visualize the results over time. For that, we will follow the same steps that we have followed for the first principle approaches. That is, first set up a computational domain and grid, then define the blob shape, and then initialize a PDE model to simulate how the blob diffuses and moves due to advection. We will also specify the coefficients for diffusion and advection, apply the boundary conditions, and solve the PDE over a specific time span. Finally, we will animate the results to show how the blob evolves over time. So first, let's define the computational domain dimensions, that is X, E, and YE, and create a even more finer mesh grid dx and dy. So for this purpose, let us specify XE as 1.0. We are using the same grid grid parameters that we have used so far. So XE is equal to 1.0. I am posting the codes in the chat so that it is easier for you to follow along with me. So XE is equal to 1.0 and YE is also equal to 1.0. So this makes our domain a square domain. Next, we will specify the cell size X for a finer grid. So here we are going to use dx is equal to 1 by 100. So far in the first and the second cases, we have used dx is equal to 1 by 10 and dx is equal to 1 by 50. But here we are going for even more finer grid. So we are using dx is equal to 1 by 100. Similarly, dy is specified as 1 by 100. So we have a square domain and we have a square cell. Next, we will specify the variable nx for the number of cells in X. So nx is equal to xe by dx. And then number of cells in Y, that is ny is equal to ye by dy. So now we have defined the computational grid. Now let us initialize the pollutant distribution. So for this purpose, we will define the radius and the center of the block. And then we will create a grid using mesh grid and set an initial field F to 0. So to specify the radius of the block, R is equal to 1.5. The radius of the block is R is equal to 1.5, and the X coordinate and the Y coordinate of the blob center, that is X cent, is equal to 0.5, as we are placing it in the center of the domain. Similarly, Y cent is equal to 0.5. So now we have specified the radius and the center of the blob, and the mesh grid and the field is already added in the work-life script. So for the mesh grid, we are using same linspace is of 0, xe, nx plus 2, and linspace 0, ye, ny plus 2. The plus 2 is to account for the boundary conditions. Then we are initializing a field f of zeros with the dimensions of ny plus 2 and nx plus 2. And we have also defined the blob shape, which is the parametric equation of a circle. So this initializes the pollutant distribution of a circular blob within the domain, providing us a clear starting point for tracking its evolution during the simulation. Now next, we'll create a PDE model, and the geometry is defined and decomposed. The geometry is then set for the model, and a mesh is generated for the numerical computation. So to create the PDE model, we use a variable model is equal to create PDE. So in line number 241, we are using a variable model is equal to create PDE. Next step is to define the geometry. And we are specifying the geometry x as a variable geometry is equal to 3 semicolon 4 semicolon 0 semicolon xe xe 0 0 0 ye ye. Then we are specifying the decomposed geometry. So for this purpose, we are using the function DECSG of geometry. So for the decomposed geometry, we are using the function DECSG of geometry. Next, let us set the geometry for the model, and we are setting it from the edges. So for this particular reason, we are using geometry from edges of model, G. The next step is to generate a mesh for the model. So for that purpose, we use generate mesh of model. I hope you are able to follow along with me. So we have entered the code to generate the mesh for the model, that is generate mesh of model. So this sets up the computational framework needed to simulate the advection and diffusion processes within the domain. Now let's set the initial conditions for the PDE model using interpolation to the interpolation to map the initial blob shape onto the grid. So for that reason, we have this code that sets the initial condition for a model using a function handle that interpolates values from a grid based on the specified location. This particular line of code utilizes a function handle to define the initial conditions for a model. It uses um, interp2 function to perform a bilinear interpolation on a grid defined by xg and yg using the values from the field f. The interpolation is done at the coordinates specified by the location.x and location.y with a default value of 0 for points outside the grid. So this approach allows for a smooth transition in initial conditions based on the underlying data. So now let's define the advection velocities in x and y direction along with the diffusion coefficient. So for this purpose, we will be using a function cfunc to specify the coefficients for diffusion and convection, which are then applied to the model. So for the x direction velocity, we are using the variable vx, and we have used a very small value of 0.02 so that for stability. So specify velocity in x direction as vx is equal to 0.02. The velocity in y direction is 0 because we are assuming that there is no upward movement. So v of vy is equal to 0.0. And next we will be defining the PDE coefficients, that is the diffusion coefficient, to increase the stability, reaction term, source term, time dependent term. So first coefficient is the diffusion coefficient. For this, we are using the variable diffusion, which is equal to 0.005. So in line number 264, diffusion is equal to 0.005. Then the next coefficient is the reaction term. We are assuming A is equal to 0 for the reaction term. So in line number 266, add A is equal to 0. Then the source term is F underscore PDE, which is equal to 0. So for line number 268, right, F underscore PDE is equal to 0. Then the last coefficient for PDE is the time dependent term. And here we are taking it as D is equal to 1. So in line number 270, you have to write D is equal to 1. So after that, we have a code that is defining the coefficients for the partial differential equation, that is the PDE model, and also incorporates diffusion and convection terms based on the specified parameters. So we the coefficients that have been used here is M, which is 0, indicates that there is no mass coefficient. D, which is set as D, sets that the diffusion coefficient to the value of D. The CFUNC assigns the previously defined convection coefficients function. A is specified as A, which specifies the reaction coefficient. F is the F underscore PDE, which defines the source term of the PD, which can represent external influences or sources within the system. So this structured approach allows for a more comprehensive definition of the physical process modeled by the PDE and enabling simulations that account for diffusion, convection, reactions, and external sources. Now, let's apply the boundary conditions. So for here, we are using the Dirichlet boundary conditions and 0 at boundary. For that purpose, in line number 288, we will add the code, apply boundary conditions. Model is Dirichlet, edge is 1:4, U is 0. Then we will specify the time span and solve the PD over this particular time range to produce the results for each time span. So time span is equal to, we are using the variable T list, which is time space of 0. Which is T list is equal to line space 0 to 100 at a time step of 0.25. So we are using shorter time and more frames so that it's easier to observe the simulation. Next, to solve the PDE, we will write results is equal to solve PDE. And in brackets, we have two arguments, that is model and T list. So to solve the PDE, we have results is equal to solve PDE model comma T list. Then we have a code that will create an animation of the result. It iterates through each time step, plotting the solution and updating the figure to visualize how the blob changes over time. The axis limits and the color limits are also set for clarity. So let's go ahead and run this particular section. So I hope you're able to observe how the initially circular blob is getting so here we could see um, how we could model and visualize the dynamics of a blob in a two-dimensional space using the MATLAB PD toolbox. So in summary, the PD toolbox provides a powerful and flexible framework for simulating the transport phenomena such as advection and diffusion. And by leveraging its capabilities, we can efficiently explore the evolution of scalar fields, such as movement and dispersion of a blob under various physical conditions and boundary constraints. So with this, we come to the conclusion. So in this particular hands-on session, we saw that this simulation provides a clear step-by-step approach of modeling pollutant that moves and disperses in a river channel. By initializing a concentrated spill and simulating its transport with a realistic velocity field, we can visualize not just the downstream movement, but also the gradual spreading and dilution caused by the advection and eventually diffusion. The concentration profiles at the two sensors vividly illustrates how pollutants first impact the locations near the spill and over the time reach farther and more peripheral areas such as the riverbank. So by monitoring the concentration at multiple points, this approach highlights the importance of both flow dynamics and spatial positioning in predicting pollutant exposure. So the evolving simulation output directly supports water quality management by indicating when and where the pollutant level will peak, enabling targeted remediation and timely response. So with this, we come to the end of the today's session. So in this today's session, we saw how to generate contour, surface, and vector field visualizations in MATLAB. We used MATLAB to simulate basic velocity fields, scalar transport in 2D, and visualize the advection of a scalar quantity over time in MATLAB. We also interpreted the vector and flow data visually using MATLAB. With this, thank you for attending today's session. If you have any questions, please post them in the chat.
Priyanka ma'am.
Yes, sir.
Yeah, there was a post by Mr. Saurav Datta on the YouTube. I reposted it here. Would you like to take that question?
I think Murli sir, probably Lavesh, the TA for this course, can take this question.
Right. Lovesh, are you there?
Hello, am I audible, sir?
Yes, sir. You're audible.
Yeah, sir. Regarding this, I'll share the answer in the chat box. But the question asked that it is way beyond the scope of the current syllabus in our course. In our course, mostly we are dealing with the continuum hypothesis. Fluid, for fluid flows in the continuum hypothesis, only that we are discussing in this course. And other than that, beyond that, regarding a brief detailed answer, I'll share in the chat box.
Sure, Lovesh. Thank you so much. Thank you, Priyanka ma'am, for this session. It was very informative and helpful. And thanks to all the participants as well for joining and making the session interactive. So we are closing the session now. Thank you all.
Thank you, sir. Thank you all.
Thank you, sir. Thank you, ma'am.
Yeah, thank you.